draw a vector field. 21 through 24, they give you a scalar function and they ask you for the gradient vector field. You're just taking derivatives. That's all you're doing. So this is a very, very clean, easy. I'm going to say easy because I think this homework assignment is easy. All right, that's it. 13.1's done. I don't think I modified this homework assignment, but I know for the next section I did. So the one that appears online might be a little different. I also found a typo in the formulas. Were those formulas online? Anyone know? The formulas I handed out today?
I think they were in the CDI.
They might have been in there. Okay, if they were there, just there's a typo in them. Well, I'll bring it up later and I'll show you. Okay. Now, we got this idea of a vector field, right? We will get to that idea again. Vector fields are not gone for now. They come at the end of this section. My guess is we won't make it to the end of the section today. All right, so next class we'll get into where these vector fields are going to come into play. But to begin this section, we're going to go back almost to Cal 2 and talk about these things called line integrals. Now, line integrals is not a good name for what we're about to do. So the reason why they get the name line integrals, I forget. I looked it up one time. It has more to do with the linearity of everything than it does an actual line. So sometimes they're called curve integrals, and I think that's a better name. But I'm going to say line integrals from here on out. So let's imagine that we have a function of two variables, which we know is a surface, right? And we have a curve C in two-dimensional space. So we have this surface, okay, this surface right here. And then on the ground, we have this red curve on the ground in two-dimensional space. If I take just those points in this curve, and I just plug those points into the surface, I'm going to get a curve on the surface, right? And that's that blue curve. So if I look at this, straight from the top down, that should be a semicircle right over another semicircle, yeah? What we're interested in finding here is this. What if I make it a little bit bigger? Imagine what we call dropping a curtain down from that blue curve down to the ground. A curtain, right? What's the area of that curtain? That's the line integral of the scalar function f of xy on that curve. You see it geometrically? Understand it geometrically?
Yes.
Okay. Yes? All right. So I tell you, let's go back to Cal 2. Cal 2, we were looking at a flat sheet of paper, weren't we? And we were taking a curve, and we were dropping a curtain down, weren't we? And we were dropping that curtain down onto the x-plane or the x-axis, right? And we were trying to find this area. So we've actually done this problem, haven't we? All we're doing now is we're saying that this curve up here can live in three-dimensional space, and that means the curve on the bottom, the ground, is actually going to live in two-dimensional space on the ground. Understand that? So if you take this flat sheet of paper and you allow it to be in three-dimensional space, you have this picture, right? Do you all see that? So what did we do in order to find the area of this curtain back in Cal 2? We did little rectangles, right? We just sliced it up into little rectangles. And we did a bunch of them, right? Called these Riemann sums. And what we did is we tried to find a general formula for just one of the rectangles. So we took a look at just one of them. We said, all right, well, How tall is that rectangle? Well, it would be the function's value, right? It'd be the function's value would be the height. And then how wide was this rectangle? Dx, right? This is our width, our change in x. So this was dx. And then we said, all right, let's add them up. Let's add up all the rectangles. So how do you add up an infinite number of rectangles? Well, that's what the integral is, right? It's a sum of an infinite number of things, whatever it is. What is it the sum of? The area of this. Area is this times this, so f of x dx. Add up all these rectangles, all the areas of these rectangles. And then you go from what? A to B, because that was A and that was B. Yes? Okay. We need to do the same exact thing. What's the problem, though? What's the difference for us? What's not going to be the same? The what?
The domain.
Yeah, the domain on the ground, right? So you know how we said the width of this rectangle was dx? That's because the only thing changing was x, right? But if this curve is on the ground, the x and the y are both changing, aren't they? So how are we going to deal with that? That's me just saying basically what I just drew on the board. So now let's take a look at that curtain, and I'm looking at one little rectangle, all right? That little rectangle. How tall will this rectangle be? It's the function again, right? Same thing, but see, this is a scalar function of two variables. So it's not f of x, it's this is f of xy, right? And then this is the critical part. How wide is this? dy dx? Close. Close. Okay, so what I'd like to do is I'd like to take a look at that red little arc right there, right? And I've got a little rectangle that's cutting across, going from one point to another on that, right? That's very close to the arc length, isn't it? Isn't that little segment approximately equal to the length along that arc? So and then when we go to the infinitesimal, when we let this rectangle get really, really narrow, the error that we have in here gets smaller and smaller and smaller, so it actually is the arc length. That's exactly right. So this little thing is, I'm just going to say arc length for now. And so we should have, to add up all these rectangles, it should be an integral f of xy. That's the height of the rectangle, and the width will be arc length, right? Understand? But the question is, what is the arc length? Okay? And what's my integral going to go from? What to what? So I'm going to resolve that now, but just want to make sure you understand what's going on here. Any questions? All right, so now what we have to do before we can actually finish this up is we have to get some stuff out of the way that you may or may not have seen in Cal 2. Whoa, where did that come from? Is that taking me to the next page? Parametric curves. Now, we did talk a little bit about this earlier in the semester. Let me make sure I'm going to use the same variables. R, are we going to use R, X? Okay. So, parametric curves. Let's say I come in here and I tell you right now, X is equal to cosine t and y is equal to sine t. We look at this as a set of equations, all right? If I let t right now vary between 0 and pi, what will the set of equations draw me in two-dimensional space? Half of a unit circle, right? If I plug in t as 0, cosine of 0 is 1, sine of 0 is 0. So I would be at 1, 0. And then if I plug in, let's say, pi over 2, I'll be up here. If I plug in pi, I'll be over here. And all the values of t between 0 and pi, you draw the upper half of the circle. That is an example of a parametric equation. What it is, or a parametric curve, it's a curve that you draw using the parameter t to draw it. The difference between that and something like this, y equals square root of x, this is not a parametric curve because for this, the relationship between x and y is actually between x and y. There's no parameter here. You have to give somebody x in order for them to determine y, right? Here, I have to give you x to get y. Here I have to give you x is 4 to get y is 2, right? And you put those together and you draw it, right? And you get, in this case, you'd say this is a function of x. Here, x and y are independent. I can still get x. I can get x if someone gives me t, right? I don't need to know what y is to get x. I just need to know what t is. I get y by someone telling me t. So you see there's not that relationship that you have over there where one of them gives you the other. So we like parametric curves because they allow us to do something that you cannot do with this. Let me give you a full example. What if I wanted to draw the unit circle without allowing you to do this? Okay? Well, the only way you could do this is by telling me the equation of this circle. You would tell me x squared plus y squared is 1. I'm saying this is a unit circle, okay? Can you write this as a function? You would have to solve for y, wouldn't you? And when you did that, at some point you'd have to do plus or minus. And then you get 1 minus x squared. And that is not a function because you have one input goes to two different outputs. And we could tell that by just drawing a vertical line and running the vertical line test that we learned in college algebra. Yeah? I'll just give you one more example of this. If I plug in 0 for x, what comes out for y? 1 or negative 1, right? So if I plug in 0 for x, it's going to spit out this number, and that's why it's not a function. You have one input, two outputs, not allowed for functions. But if you do a parametric curve, can you draw me a circle? Yeah, I just need to extend this out to 2 pi, right? And now I can come all the way around? Is this a function? Yes? Why is that? They're the same picture. Why is this a function and this is not a function?
You only have one output for every t.
For every t, there's one output. See, look over here. This is not a function. This is what we normally say. This is not a function, but we always leave this part off, of x. It's not a function of x. If you plug in x, you're going to get two outputs. So it's not a function of x. Over here, this is a function. This is a function. What's the thing we're plugging in? Of t. Now let me explain why. Because some of you know it, some of you see it already, but let's just take this point up here and down here. Those points over here, why? I mean, it fails the vertical line test, right? But see, you don't run a vertical line test. You only run vertical line tests when you're checking to see if something is a function of x. So over here, What input, what t value gives me this point up here? Pi over 2. What input over here gives me this one? 3 pi over 2. I heard negative pi over 2 also, right? But I was between 0 and 2 pi. So look, I can get to those 2 points, right, with 2 different inputs. And no matter what, I plug in different values of t, it's never going to take me to 2 different places. So I can draw a circle, and it still qualifies as a function. And that's what we like. We like this sort of thing because, well, it kind of sucks when we have to worry about vertical line test. And the whole idea of the function goes away. So parametric curves allow us to draw curves in 2-dimensional space. All right? And complicated-looking curves. So what we normally have for a parametric curve is this. We have x is usually some function of t, and y is usually some function of t. Oh, y is equal to some function of t. So they both depend on t. That's what a parametric curve would look like in R2. What about in R3? You would have z as a function of t also. And you could then draw curves in 3-dimensional space. Now, for those of you who own graphing calculators, there's a button on your graphing calculator called Mode. And you can actually change your function. If you go to Mode, I believe there's something about graphing in there, and it gives you like function. What's another option? Polar, and then parametric. And there's other ones in there depending on your calculator. But your calculator does have a parametric mode, and I encourage you to go in there and learn this mode. If you come by my office, I'll show you how to mess with it. You actually can throw this completely out of your calculator and never use this again in your life and just use parametric mode. And you can do everything you've done before. So let me explain how that would work. Let's say that I wanted to graph the function f of x equals the square root of x. Well, we all know that that means that y is equal to the square root of x, right? So y depends on x. What does x depend on? Nothing, right? What I'm going to do is convert this to a parametric curve instead. So I just need to come up with some function for x and some function for y. They both have to depend on t. Well, the x doesn't depend on anything, right? So I'm just going to let that be t. And then the y is going to be the square root of x, but that's just t, root t. So if you go into your graphing calculator, you go to parametric mode, you put in, I think your calculator says something like x1t, y1t, or something like that. And then the next one will say x2t, y2t. That's so you can draw multiple ones if you want to. But if you put in t, and you have to use t, not x, you put in t and root t, and you graph it, it should draw you the same curve as you writing square root of x in. There is a little bit of a thing you have to be careful with. Most of these calculators, by default, put your t between 0 and 2 pi. So there's a window option where you can change your restrictions. Change your restrictions on t, and you can make it go from like -10 to 10, and then it would be pretty much the same as the regular graphing calculator. Okay? This is just bonus information for you. So with that in mind, what if you were given an equation like this? X is equal to cube root of y. X is equal to y squared plus 1. Back in Cal 2, someone might have asked you to actually find like the area between these two curves. And then you would have to be able to draw them. And a lot of people struggle to draw these because, sorry, hold on. These are two different curves. Let's just do one at a time. Let's just do that one. So you struggle to draw them because your calculator in function mode, you can't put that in. And so there were some problems. I'm claiming right now that if you use parametric curves, you can do this. So what could I do for my parametric?